Hello, and welcome to Module 3, where we will focus on numerical descriptive measures, looking at how we can use data as information. With our understanding of statistics, we can start to inform our decisions using our analysis. First, we will look at central tendencies and the relationships between different data points. We will measure the mean and percentiles to look into dispersion. We will cover the Sharpe ratio, Chebyshev's theorem, the empirical rule, and start introducing z-scores, which will be a theme going forward for the next few modules. Lastly, we will measure the correlation between variables and how to measure the relationship between them. Let's dive in. When we say central tendency, we're talking about where does the data tend to cluster around some value. We're looking to understand what is the typical value that you'd expect to see. And this is what would be used to describe some tabular data. There are examples of central location for many things, such as the average return on an investment, the number of defects in a shipment, the expected salary for an MBA, and so on. We use the mean to measure central location. We can consider this the average, or where the data tends to cluster. This building is a church in Reykjavik, Iceland, and the middle height would likely be somewhere in the middle of all towers. I just think architecturally is a cool building, and it'll start to show what it is we'll be looking at when it comes to central tendency, because this design is a perfect example of that. When it comes to calculating the mean of a variable, such as the tower height in this image, we would add up the height of all the towers along the facade and then divide by the total number of towers. Let's consider a case study where you are making the decision between two mutual funds as an investor. One is the growth investing, the other is value investing. Growth funds are expected to grow at a faster rate compared to the overall stock market. Compare this to value, which are stocks with a price below the potential or true worth of the stock. The main component of return is the increase of the stock value in growth funds or through dividend income for the value funds. So let's analyze the annual return for the different mutual funds from 1984 to 2019. Here is a time series of the annual return in blue for the growth stock. In red is the value fund performance. We see some particular trends with a dip around 2008 during the financial crisis. It also appears the growth fund had a peak and then fell between the year 2000 and 2003, whereas the growth fund remained more steady. What if we want to know on average which fund performed better? We take the annual return for every year in our sample and then divide that by the total number of observations. Over a 36 period cycle, the mean return for growth was greater than the mean return for value. However, this really doesn't do justice to how someone might select a stock or fund, since this is over a yearly aggregate of a 36-year period. And that would mean we might put our money right in at 1985 and we would keep it there over this time period if we were really looking at this type of measurement, which might not be actually representative of what happens when you would make your decision. So the mean of the sample is referred to as X bar. We can denote the numerator of the formula using the summation notation, which is the sigma to represent adding everything in the sequence. This is our formula for the sample mean. If we had all the observations for growth since the start of the fund's existence, then we would have the population. So our analysis was only on a sample mean since it was just through 36 years. And the mean of the population is referred to as the Greek letter mu, which we'll see very often going forward from this point. Notice also the difference in the lowercase n and the uppercase n, where we assume the sample number of observations. Lowercase n is smaller than the population, as intuitively it is a subset. We refer to the population mean as a parameter and the sample mean as a statistic, since in most cases the population mean might be unknown. We use the sample mean to make an inference about the population. So let's think back to our example about the mutual funds. What if we consider the dip in 2008, where the value was around 40% annual return, negative 40% annual return? We can observe the distribution of values using a histogram to see the central tendency differences between the funds and how both funds have outliers around negative 40%, where the growth fund also has an outlier near a positive 80% annual return. When I use the word outlier, I'm talking about a value that is far away from the cluster of the central mean. And this can actually skew the sample mean. Another, to really drive this point home, when I talk about skewing the central mean when you have an outlier, consider if you were to take the average salaries of 10 random people in the room, what might that look like? And then let's say someone like Elon Musk walks in the room, the average will become very skewed, not an appropriate measure anymore to understand the average for the group. When we talk about skew, the data might also be generally skewed towards the left or to the right. Let me just make sure my screen is sharing appropriately. Okay. Perfect. All right, where were we? We can think of skew as being positive or negative. There is a function to measure the skewness coefficient in Python. A value that is 0 means there's no skew and we have perfect symmetry, kind of thinking back to that building we saw in the first slide. A value that is negative implies the bulk of the data lie to the left of the mean, and vice versa for positive. Skewed data shows the mean might not be the whole picture. We need to consider other descriptive statistics to measure the data. Another summary statistic to consider is the median, which is the middle value of a variable, with an equal number of observations to the left and to the right of that middle value. We also have the mode, which is the value that appears the most often in the data. Here's a good way to see the difference between mean, median, and mode when we have these different skewed distributions. We see in the middle, we have a symmetric distribution. The average, the middle, and the most are all at the same exact point. However, when our data is skewed either positive or negative, we see the mean is greatly affected by the skew and becomes closer to the tails compared to the highest point in the distribution that might be better represented by the mean or by the median or the mode. In order to calculate the median, we would sort all the data points from smallest to largest and then take the middle observation, as we see here. The mode is the data point that occurs the most frequent. There can be more than one mode if multiple values are the highest count. There also could be no mode if there's none that really takes the cake. If a variable has one mode, we consider it unimodal. If two or modes exist, then we call it multimodal or bimodal. When thinking about our data points, we also want to analyze the spread and distribution of values. This will be a really important concept to really understand here. The median was helpful to know what the middle value is. This can also be considered as percentiles, where we usually look at the 25th, the 50th, and the 75th percentile as some of the most telling points of information. Here's the same example data from the growth versus value fund, now visualized by the percentiles using a box plot. We see the median, which is the middle line, is actually the same between the two funds. But it's really this distribution, the edges of the whiskers from the plot that show the range of values. Notice for the value, we have a diamond that shows the outlier we saw before in the histogram. That is not included in the percentile calculation automatically. A percentile divides the variable into the different relative location. So we want to know how the data clusters and what is the relative performance between these two funds in order to inform our decision of which fund is right for you. For example, suppose you obtained a 75 out of 100 on a midterm. We don't know what that really means, actually, until we compare it with how the rest of the class did. Maybe 75, it's a really challenging class, and that would be one of the best compared to how you relate to the relative distribution. And if you scored better than your peers, are you in the 25th percentile or the 90th? To calculate, we effectively would divide the data by how many values fall within the range. For the quartiles, we take the first 25 values, the 50th, and so on. We use the box plot to gauge the shape and the distribution to assess the level of symmetry that exists. Throughout our discussion of central location, we have touched upon how the rest of the data varies around the center. For our mutual fund example, as an investor, you might wonder, why would anyone even put their money in the value fund when on average this fund had a lower return compared to the growth fund? But it turns out that the average, again, is simply not sufficient. We want to measure the underlying variability of the variable, particularly as it relates to the level of risk an investor is willing to take. First, we consider the range, which is the difference between the maximum and the minimum value. This really only provides insight, though, into the extreme values at the highest and lowest ends, and essentially ignores all the meat in the middle. If we want to know more about how the data points vary compared to the average, we can start with the mean absolute deviation, which takes both the positive and the negative values using the absolute difference, so we can actually start to see the dispersion. If we didn't take the absolute value, which negates positive or negative, it's the absolute, the sum would simply be 0, since the positive and negative would cancel each other out. We'll get more into variance and standard deviation in future chapters, but for now, we consider the fundamental of understanding the differences between the observations and the mean. The variance is similar to the MAD, or the mean absolute distribution, but it takes the squared difference from the mean. The standard deviation is then the square root of that variance, which is used to bring back the same unit of comparison. So you can start to compare apples to apples. The key difference of why we use the variance rather than the MAD is because squaring values emphasizes the larger or smaller differences, whereas MAD weighs large and small differences equally, since it's taking the absolute value distribution. To visualize why the square difference is used, check out this demonstration where we see the 5 different points with the values 1, 2, 3, 4, and 5. The horizontal bar is at 0.25, and each vertical line represents the difference between the points and the line. We see the rectangles represent the squared area, and the point at 5 in purple is the farthest away compared to the area at 0.1. And this is really how we weigh the variances. Because that value is farther away, this squared difference shows there's more difference to the mean. The image on the right shows how if we move the horizontal line up to y equals 3.7, which is the mean, the total area decreases. If we think about how this horizontal line acts as the mean, we can think how far away each value is from that line. The smaller the variance, the closer to the mean all the values are. What if we wanted to compare the variability of 2 variables with different means or different units of measurement, trying to use these same measurements to now be able to compare in a one-to-one way? We can use the coefficient of variation to measure the relative dispersion, and this adjusts for the difference in the magnitude of the mean. It is calculated by dividing a variable's standard deviation by the mean. It is a unitless measure that allows for a direct comparison of mean adjusted dispersion across the different data sets. It essentially normalizes the volatility of a standard deviation by dividing it by the mean. As we're looking at our example about the growth and value fund, we can ask the question of why would a rational investor choose to invest in value over growth, since the average return was 3% lower over our sample period? Well, the answer really lies in the variance, or in general, the level of risk for the investment. When a fund is volatile and shifting in expectations and evaluation, there could be more reward, but there is inherently more risk. This is why we look at both mean and variance. Here is a table with the average return and variance. We see that there has more variance for the growth fund, where the investor would encounter more risk. This concept also relates to the Sharpe ratio, developed by Nobel laureate William Sharpe. It is used to help investors understand the return of an investment compared to its relative risk. The ratio is the average return earned in excess of the risk-free rate per unit of volatility, or total risk. And volatility is a measure of the price fluctuations of an asset or portfolio. So the higher the Sharpe ratio, the better the investment compensates its investors for the risk of that fund. So we take the mean and subtract from it a risk-free asset, such as a treasury bill, and divide by the standard deviation. And this really gives us that metric of how much is this relative risk to the potential value that this fund or stock might result in. But when we talk about standard deviation, how can we actually interpret what it means? Currently, we have said that a low value indicates that the data is clustered near the mean, and vice versa for a higher value where it's farther away from the mean. But actually, we can use the standard deviation as a measure to understand the relative location of the rest of the distribution, specifically using Chebyshev's theorem, the empirical rule, and the z-score. But first, let's talk a bit more about central tendency. Here's a picture I took while I was biking below Pier 11 ferry in Manhattan, where I noticed on the ground a relatively distributed amount of pigeon poop. What came to mind was how it looked somewhat normally distributed. Honestly, this is what's going on in my head, and how this would be a great example for class. The question I want to pose is, what is the probability that a pigeon poops on your head given where you stand when you see this distribution on the ground in front of you? And as a passerby, where would you want to avoid? So the answer is you probably wouldn't want to stand anywhere near this location, but the closer you are to the middle cluster, perhaps that would lead to a higher chance that a bird might give you a surprise on your head. Thinking about where the birds tend to hang out and have nests, likely we're going to see this distribution have a similar pattern going forward. So we can think of this relative location as a standard deviation. So 1 foot away from that center point is 1 standard deviation away from the likelihood of you having a bird leave you a surprise on your head. So thinking about how farther from the center point you might miss that dropping. We can think about this as the area under the curve in a normal distribution. So think about that dispersion on the floor. Now we're seeing it as area of what's the probability of a bird pooping on your head. Under the empirical rule, we use the number of standard deviations away from the mean to show the probability of a value. By dividing the area under the curve into subsets delineated by 1 standard deviation, we see that 34.1% of values fall within this interval. We can take this positive or negative and say that 68.2% of values are within 1 standard deviation from the mean. We see the farther we get from the mean, the less values are present. Particularly in the tails, we see only 0.1% of a distribution would fall there. Or this would be somewhat the likelihood of having a bird poop on your head when you're 5 feet away from that center dispersion, and that likelihood is very low. It could happen, but it's low. Ever hear about the hedge fund 2 sigma? The name comes from the measure of volatility over a benchmark using forecast signals to measure against that benchmark. If we know that the observations are normally distributed, we can make precise statements about the percentage of observations that fall within certain intervals. I bring that up to just connect it back to the growth and value fund, thinking about how these different principles are used in a lot of different applications. Another way to visualize the empirical rule is to show the approximate percentage of observations that fall within 1, 2, or 3 standard deviations from the mean. So almost all observations fall in the interval of 3 standard deviations. And this is the empirical rule because when we have this symmetrical distribution, this is how it is represented by the probability of seeing one of these values. But what about when the data isn't normally distributed and we have that lovely bell curve? We can use Chebyshev's theorem to make statements about the proportion of observations that fall within certain intervals. And this is a generalizable rule that can apply to other distributions that aren't perfectly normal. The Russian mathematician named Chebyshev found the bounds for any variable, the proportion of observations that lie within k, which is just a variable we're going to use. So in front of k standard deviations from the mean is at least 1 minus 1 over k standard deviations, squared deviations. Let's go through an example. Say the sales force has quantitative scores for their performance of a company. Out of 280 team members on this sales force, the average score earned is a 74 with a standard deviation of 8. So how many employees on this Salesforce team scored within 58 and 90? You might ask if you're evaluating performance and you want to know where you stand. So first, let's think about where 58 and 90 fall relative to the mean. We see plotted here is the mean in red with 58 and 90 in yellow. So let's subtract 8, which was our standard deviation, from 74, which is our mean, which is 66. And that would be just one standard deviation, since we only subtracted 8, which was one standard deviation. Now, if we wanted to take 2 standard deviations, we would subtract another 8 and get 58 exactly. And this goes on the other side of the axes for the positive of 90. So these values are 2 standard deviations from the mean, since we took 8 and multiplied it by 2. And using Chebyshev's theorem, we would say k equals 2, and we would have 1 minus 1/2 squared, which equals 75%. So in other words, at least 75% of all the scores for the sales force fall between these intervals. So out of 280 team members, 210 of them would score within 58 to 90. And you would have some that really exceed this and some that fall below this interval. But again, those are smaller tails. So there's not as many employees that scored outside of this middle chunk. But since this is normally distributed, we can use the empirical rule to calculate how many team members fell between the intervals. So taking that generalizable rule, and now since we know the distribution is normal, we can use our more rigid formula, which we see in green, the proportion 1 standard deviation away from the mean, where 68% of all observations would fall between. Now, what if we want to know how many team members scored above 90? We want to know who's really accelerating beyond the average. Since we know that 90 is 2 standard deviations above the mean, and 95% of values fall within 2 standard deviations, we can subtract the rest of the area under the curve, which is 5% for both tails, since the total area under the curve will equal 1 or 100%. And this would be the number of employees that score below a 58 and above 90. So we divide that 5% by 2 to account for the 2 tails on both sides of the normal distribution. And that would create 2.5% of employees scored below 58 and 2.5% scored above 90. So about 7 employees, just bringing that back to the values that we're working with, going from 2.5% of all employees here of the 280 would be 7 employees scored below this and above these 2 intervals. The main difference with Chebyshev's theorem and the empirical rule is that the empirical rule only works when the data is beautifully symmetrical and bell-shaped as a normal distribution like this, where Chebyshev's theorem asserts that at least 75% of the employees scored between a 58 and 90, whereas the empirical rule states 95%, because we have this level of precision we can take because we're assuming the data is normally distributed. And we can use the empirical rule if the histogram shows a normal distribution. And later in the semester, we'll go about how do we test for normalcy. But for now, most instances, we're going to assume the data is normally distributed, so we can use this empirical rule. Next, what about relative location within a distribution? Outside of the standard deviation for distribution, we use the z-score to now be able to compare across relative positions. To calculate the z-score, we subtract the observed value from the mean and divide it by the standard deviation. And when I say the relative, it means now we can compare between the different funds because they would have different values, and we'd want to know between them, what is this type of z-score? Because it really gives us this unitless way of understanding the differences between different variables. And the z-score is a unitless measure. Since the numerator and denominator have the same unit, it measures the distance of a given observation from the mean in terms of standard deviation. For example, a z-score of 2 implies that the given observation is 2 standard deviations from the mean. Converting observations into z-scores is also a way to standardize the data, since there is no need for units. Now we can compare performance of this sales force to the other product categories sales force or other teams throughout this company if they scored all their employees using some type of metric. So the z-score is also used to identify outliers. If the observation falls outside of 3 standard deviations, we consider that value to be an outlier or very rare to happen. Thinking back to our example about the growth and value fund, we can visualize what 3 standard deviations below and above the mean would look like and see that in 2008, the annual return reached below -42%, and therefore we can consider it an outlier since it fell outside of this normal distribution going back to this curve where most of the values were between the 3 standard deviations above and below, but now that tail is capturing this rare events that might be considered an outlier. Such observations should be reviewed to determine if they should remain in the data set. Thinking back to that Elon Musk example and taking the average income, having an outlier like Elon Musk would not necessarily be representative, but in other cases like this, it's actually important to see that the value drops so low in this area if you're trying to measure all the overall volatility. The last point of numerical descriptive measures we will look at is measure of association. And this would be used to quantify the direction and strength of a linear relationship between 2 variables, x and y. When there is a linear relationship, we can look at something called covariance. The value can be negative, positive, or 0. And covariance, when it's a negative value, this would indicate that a negative linear relationship exists between 2 variables. So if x is above the mean, then y will be below the mean and vice versa for positive. Positive covariance would indicate that both variables tend to be above the mean. If the covariance is 0, the variables simply have no linear relationship. But the covariance is difficult to interpret because it is sensitive to the units of measurement as opposed to z-score, which is not. We can tell that the relationship is positive, but we cannot compare the strength of the relationship when the units are different. A more effective measure to interpret is the correlation coefficient. It describes both the direction and the strength of the linear relationship between 2 variables. We see on the left shows the covariance and how the linear relationship would look like for negative or positive. On the right, we have the correlation of variables, and we can consider that the measures are unit-free. We're just looking at the coefficient. The value of the correlation coefficient falls between -1 and 1, where 0 would mean no relationship. The more positive the coefficient means the more positive the relationship and vice versa. So we can really start to understand using our scatter plots that we learned about last class to how do these different variables relate to each other. One thing to note is that just because two variables seem to be correlated does not mean we can make any conclusions about causation to say X causes Y. If we do see this correlation without any causation, we can call this spurious correlation. For example, the US spending on science, space, and technology is 99% correlated with suicides by hanging, strangulation, and suffocation. But we shouldn't assume that the more the US spends on science, that the more of these incidents are likely to happen. This I just took from a website where he just developed a bunch of different spurious correlations. And this one I just think is interesting that they're almost precisely similar, but we can't say these two things cause each other. They're just correlated. So we need to be careful when we're looking at our data and making any types of interpretations from it. So in this class, we talked about different levels of central tendency, how we would measure something like growth and value funds beyond just the mean. We talked about how using variance, standard deviation would give us this understanding of how likely we are to see a value. Similar with the bird poop example, how likely are you to have that happen to you the farther away you are from that central clustering? We talked about the Sharpe ratio, which looks at how much risk or volatility we might expect to see. And we talked about outliers, where we can understand how far away something is from the mean. And is this a very rare event that should be considered in our understanding of a variable? Or is this something that's an outlier and very different from everything else? So in the next lecture that I will record, I'll walk through Python and talk about how we would actually calculate a lot of these things that we discussed today.